Wow, go on, my GCSE science students. Welcome back to another video. Now, in today's video, we're going to be looking at chemistry paper 1, chapter 2, which is entitled the periodic table for the AQA science board. Okay, so there are quite a number of topics to get through, so let's get started. So, we're going to be looking at the development of the periodic table, electronic structures and the periodic table, the alkali metals, the halogens, explaining trends, and for my triple science students in this chapter we're looking at the transition metals. Okay, and that's for triple science only. Okay, good. So let's get started. All right, so the periodic table, as you can see here, right, was not looking the way it always did. All right, so the modern day periodic table, it contains all the elements, containing all their elements arranged in terms of their atomic number and their properties. Okay, but this was not always the case. All right, so this is an idea as to what the original periodic table looks like, and as you can see, you can realize that they were missing elements. Okay, so in 1808 these were all the elements known about at the time, and also the atomic structure. Not much was known about the atomic structure in terms of protons, neutrons, and electrons. Okay, so you can definitely see that there were certain differences there, and also scientists at the time, they did not know the difference between elements and compounds. Okay, so they were getting confused about elements such as like sodium, magnesium, and confusing them with compounds. Okay, good. All right. So one of the first scientists to really do some work on this in terms of elements was John Dalton, okay, in 1808. And what he did, he ordered the elements by mass. So you can see here, this is an idea as to what it looks like. So you had hydrogen in terms of mass of 1. Then you have, well, this would be strontium, currently strontium 46, and so forth. He ordered them by mass. And he also made some proposition. And one of the things that he said is that atoms cannot be broken down into anything smaller, which we know is not the case because currently you now have protons, neutrons, and electrons. So that idea was not necessarily, or is not correct. Atoms of a particular element, they're alike in every different, they're identical in every way. Okay, and that again was not true. Okay, that was not true because you had things such as isotopes. Okay, go back to chapter 1 video if you don't know what isotopes are. Also, he said that in a chemical reactions the atoms are rearranged. Okay, and we definitely agree with that. All right, good. But we did not agree with the first one because you had things like protons, you had things like neutrons, and you had things like electrons. Okay, too easy. All right, now after John Dalton, we're now on to John Newland, who he still stuck with the idea of John Dalton by ordering the elements by mass. Okay, but he also realized that there were certain patterns. The patterns were repeating themselves after every eighth element, almost like in music where you have do, re, mi, fa, sol, la, ti. That's it. So every eighth element, it was repeating the note. Okay, law of octaves. And as a result of that, you can see order the elements in terms of 1, 2, 3, 4, 5, 6, 7, 8. All right, along with that idea of ordering them by mass. Now, after that, along came Dmitry Mendeleev. Now, it's one of my favorite scientists here. Okay, so Dmitry Mendeleev, he kept the order of mass, but he also did some switching of elements. Okay, because he found that there are certain elements that their properties did not match. So what he did, he left gaps, and this was a profound thing that Dmitry Mendeleev did. He left gaps for elements that were not yet discovered. So you can see the blank spaces there. Those were gaps for elements not yet discovered. But he could make those predictions, and he started swapping around elements that he think previously did not match up. Okay, good. So that was the main thing that Dmitry Mendeleev did. He left gaps for the undiscovered elements, and he switch positions for elements that in terms of reactivity were not matching at the time. Okay, and then later in the 20th century, more modern, all right, he discovered After they discovered about the atomic structure and protons, Henry Moseley, he decided that in terms of the periodic table, he was going to put them in the order of proton number. Not mass number, but proton number. So currently the periodic table is ordered in terms of proton number and not mass number, all right? And there's some examples there that you can, if you look at your periodic table, you realize that, like, look for iodine and look at the element which comes after iodine, you realize that they do not go in that order of mass number but proton number. Okay, so in terms of summary, John Dalton, he ordered the elements in terms of their atomic masses. Then John Newlands came about and he kept that order, but he discovered that the pattern was repeating itself every eighth element. However, Dmitri Mendeleev realized that even though yes there was a pattern, he said that there were elements that were not yet discovered, all right, and he left gaps, okay, for the undiscovered elements. And then Henry Moseley, now the modern periodic table was ordered by the proton number. Okay, so that's a summary of the history of the periodic table. Now, what we're going to be doing, we're going to be looking at group 1 elements. Okay, so if you have a look here, if we look at the electronic configuration, if you don't know what electronic configuration is, you need to go back to my chapter 1 video. All right, so you can see here lithium is 2 1, sodium is 2 8 1, and potassium is 2 8 8 1. Okay, so because of this, they react similarly because all of these elements, they have one electron on their outer shell. Okay, so they have one electron on outer shell, which means that when they react, they only need to lose one electron. So they only need to lose one electron. So they're quite similar in terms of how they react. Not in terms of the rate of reaction, but in terms of the products of what they form. Okay? Good. So these are now called my alkali metals. So group 1 elements, they're called alkali metals. So right here, group 1, they're called the alkali metals. Now, why is that so? We're going to look at why exactly is that so. But before we look at that, let's just look at the other groups. So we have the alkali metals. Right here, you have your transition metals. Okay. Then you also have this group here, the halogens. And then you have group 0, which is called your noble gases. Okay. Good. So elements are placed in groups because they have similar properties, okay? And group 1 is no different because they have the same number of electrons on their outer shell. Also, to know the difference between your metals and non-metals, think about the step line which is found here. All right, so to the left of that step line, all of those are metals, and to the right of that step line, all of those would be non-metals, okay? Good. All right. Now, when you think of metals and non-metals, it is very important that you know the difference between the two. Okay, so metals, they form positive ions, which are called cations. Remember, cats have paws. That's what I used to remember. And then negative ions, they have anions. Okay, metals are shiny. They're malleable. Malleable just means that they can be bent into shape. High melting point. They're magnetic, such as iron, nickel, and cobalt, and they're mostly solid at room temperature except for mercury. Okay, and on the flip side you have your non-metals, which are dull, brittle, low melting point, not magnetic, and mostly gases at room temperature. Okay, now how is it that these metals react with water? And we also need to know the general word equation. All right, so before we look at that though, quickly, let's look at some group 1 properties. They have low melting and boiling points in comparison to their metal counterparts. They're very soft, so you can cut them easily with knife. They have low density. What does that mean? They tend to float, okay? They tend to float on the liquid. They're very, very reactive because they have to use one electron from their outer shell, and when they react with water, they produce the corresponding hydroxide and hydrogen gas. Okay, they form alkaline solutions, which means that they have a pH of greater than 7 when they react. Strongly alkali solutions, okay, which is why they're called alkali metals, because they form alkali solutions, okay. So when metals, group 1 metals, react with water, they form their corresponding metal hydroxide and hydrogen gas. And this metal hydroxide is the reason why it is an alkaline solution, which is why they're called alkali metals, okay? So let's see if we can write an equation for this. So lithium, capital letter, lowercase, lithium solid, it will react with water, which is H2O, and that's a liquid. So put our state symbols in. These are called state symbols. Arrow, so it will form lithium hydroxide. So that's LiOH. If you're not sure how we got that, so it's Li plus OH minus, equal and opposite, they cancel out, you put them together, so it's LiOH. You need to know your complex ions. I have a video there about writing formula of compounds, and it will also form hydrogen gas. Now many students will want to just put H, but hydrogen doesn't exist as H by itself, it is H2. All right, now straight away this equation here is not balanced. So to balance that equation, you can watch my video on balancing equation as well. We're going to put a 2 here, which now makes it 2 lithium and 4 hydrogen. So this 2 affects the hydrogen there and another 2 hydrogen there. All right, good. So we're going to put a 2 there to make it 2 lithiums. Okay, good. And I now have 4 hydrogens. I'm going to put a 2 there, which now makes that 4 hydrogen. And I now have 2 oxygen. Equation has been balanced. Okay, good. So if you're not sure to balance equation, I have a video on balancing equation. Please go and have a look on my YouTube channel. Okay, good. So this that is formed here is called lithium hydroxide. So if you have a look, sodium will react to form sodium hydroxide and hydrogen, and potassium will react with water to form potassium hydroxide and hydrogen. Have a go at writing those balance equations, okay, with state symbols. All right. Okay, let's start again. So on this slide, what we're now looking at is what will happen when lithium, sodium, and potassium reacts with water. They all react differently, but as you notice, the reactivity increases as you go down the group. So lithium, when reacted with water, you can notice that lithium floats. Okay, lithium floats. You will also see bubbles. Some textbook will say effervescence, fizzing, anything like that, still bubbling. Also, we could test the gas. We could collect the bubble and test the gas with a glowing with a lighted splint rather. So lighted splint makes a squeaky pop sound, and that means that hydrogen is present. So lighted splint makes a squeaky pop sound. And also, if we add some universal indicator liquid, it becomes purple. So UI becomes purple. Now, all of these are observations when you react the metal with water. As you can see, sodium, there's more bubbles still floating. Okay, so it's faster, rapid fizzing. Okay, so you can see rapid fizzing there, and also it would make a squeaky pop sound with the lighted splint. And finally, look at that one. You can see a flame. Okay, also floating. All right, so you can see as you go down the group, it becomes more reactive. Okay, good. Now, why is it that it becomes more reactive? In order to know why it becomes more reactive, you need to think about the following when answering questions about this. So, as you go down the group, the atom gets bigger. Okay, so as you go down the group, the atom gets bigger. And remember that in order for group 1 metals to react, they need to lose their outer electron. Okay, but that outer electron is held on by the protons in the middle of the nucleus. Okay, because opposites attract and the protons are positive, which therefore means that because they're being held down by the proton, the one which loses its electrons easiest is going to be potassium, okay? Because you have the shields here. So the proton cannot get to hold on to that outer electrons as strong as it would like. Therefore, the outer electron is easily removed, okay? So we can summarize this as we go along. So as you go down the group, well, alkali metals, they definitely need to lose one electron. The nucleus is positive because of the proton, and therefore and as you go down the group, there are more electron shells, and therefore it becomes easier for it to lose an electron. All right, so the electrons are negative, and the attraction to the nucleus becomes less because you have more shielding, and therefore reactivity increases as you go down the group. Okay, you can pause the video and make sure you take those key points down. Now, alkali metals, they also react with oxygen to form metal oxides, which dulls their surface. Okay, now the general equation is as follows. So the alkali metal plus oxygen will form the alkali metal oxide. For example, lithium would react with oxygen. Please note that oxygen is not O, it is O2 because it's diatomic. Oxygen doesn't exist as O, and it will form Li2O. How did I get Li2O? Go to my video about writing formula. So this is 2 minus, as it's in group 6. You stop, you remove the charges, you drop, you swap. Okay? Too easy. So that now becomes 2, that becomes 1, so it's Li2O, okay, and that's a solid, that's a gas, and that's a solid. Straight away you should realize that this is not balanced. This is 2 here. We need to put a, well, before we get there, let's clear that. Good. All right, so we have 2 oxygen there. We only have 1 on this side, so the number that we need to put there is 2, which now makes the oxygen 2, but now my lithium becomes 4, so I have to put a 4 there, okay? And therefore, that's my balance equation. Try for sodium and try the equation for potassium to get your practice in, okay? And there's my answer right there. All right, good. Also, the alkali metals, they will react with chlorine to form metal chlorides. Now, what's the general word equation? Here it is. So sodium plus chlorine will form sodium chloride. So the general equation is as follows. Alkali metal plus chlorine will form your alkali metal chloride. So let's think about the equation for this. So it's Na plus Cl2. Chlorine again is diatomic. It will form NaCl. Straight away it's not balanced, so we put a 2 there and a 2 there to make it balanced. How did we get the formula for sodium chloride? Group 1, so it's positive 1. Chloride is group 7, so it's negative 1. Therefore it's NaCl. Okay? Good, and that sums it up for group 1. Next up, group 7. The halogens, okay? So you can see the members here of group 7, and what's common about them is that they all have 7 electrons on their outer shell. So you have fluorine, chlorine, bromine, iodine, astatine. Too easy, okay? Now, what's happening as you go down the group? Now, as you should see, as you go down the group here, the atom is getting bigger. And also, they all need 1 electron for them to be stable. Okay, so 1 extra electron on that end would then make that atom stable. So if we think of that as the electrons trying to go in, right, remember that they would form negative ions. All right, good. So they all have similar properties, okay? So they would react in a similar manner, similar to group 1, how they react in a similar manner. Group 7 would react in a similar manner. But remember that these are now going to form negative ions when they react, all right? So here are some properties of group 7 elements. Can you spot any pattern? Okay, straight away, as you go down the group, you move from a gas to a liquid to a solid. The color becomes dark as you go down the group. The melting point increases, the boiling point increases, okay? The reason the melting point and the boiling point increases is because of the intermolecular force is increasing between the molecules. Okay, good. Now group 7 elements, they often undergo a type of reaction called displacement reaction. Now what's a displacement reaction? A displacement reaction, as it suggests here, is a reaction in which a more reactive substance take the place of a less reactive substance. All right, and that can be summarized here. So if you have a look at A being bonded to B and C comes in, C can take the place of A, okay, because C is bigger and more reactive. Okay, so that's just a general example. But let's look at an actual example of a displacement reaction. Now, in a displacement reaction as it relates to the halogens, the more reactive halogen can take the place of the less reactive halogen from its salt. So for example, if you have fluorine, which is found at the top of group 7, which is the most reactive. So you have fluorine, chlorine, bromine, iodine. All right, that one here is the most reactive in group 7. Okay, and this one here is the least reactive in group 7. Okay, so you have a most reactive, least reactive. Good. Fluorine can take the place of chlorine from the salt, and therefore it will form sodium fluoride, and chlorine is knocked off by itself. Also, please try and be able to write equations for these reactions. Okay, good. So let's go ahead and just try and write that equation quickly, because what's chemistry without writing the equation? So fluorine would not exist by itself, so it's F2. It's going to react with sodium chloride, and it will form NaF. Okay, good. And then chlorine would be by itself, Cl2. So straight away you realize that that's not balanced. All right, let's use a different color here. So you're going to have 2 there and 2 there, and then equation would be balanced. Okay, good. All right, good. So that's the reaction there. Now, to prove which one is more reactive than, which halogen is more reactive than the other halogen, we do what is called a displacement reaction in a dimper tray. Don't know if you remember doing that, but what we will have here, as you can see here in the first column here, distilled water. So in essence, what we have here are all our halogens. So you have chlorine, bromine, and iodine, all going across like that. Okay, and then to each we're going to be adding water as one. So the reason why the water is being added down this end, so in this one here we're going to be adding water. Okay, and the water is just to allow for comparison to be made. Okay, good. Then in your next column here you're going to be adding, in this one, in this bit there, you're now going to be adding potassium chloride, okay, followed by potassium bromide, followed by potassium iodide. And then you want to compare to see what the color changes have occurred. All right, so you can see at the end of the reaction, you can see here, firstly, in the water column, no color changes. Obviously, potassium chloride would not react with chlorine. That's why that is blank there. Good. And then bromine, okay, with potassium chloride, no change there. But look at where you're having your color changes. Now the color changes is happening. I'm just going to look at this one. Why is it that the color change happened there? And we need to look at that. So let's go. Let's use that color there. So if you think about it, you're adding chlorine. Okay, so just remember fluorine, chlorine, bromine, iodine. So where your fluorine is more reactive, okay, your fluorine is more reactive, your iodine is less reactive. Okay, so if you add chlorine to potassium bromide, and let's use a different color for the potassium bromide here. All right, what will then happen is that your chlorine, which is more reactive, will knock away. So your chlorine, which is more reactive than bromine, you're going to end up with potassium chloride and you're going to be ending up with bromine by itself. Okay, you're going to be ending up with bromine by itself. Okay, plus bromine. Now, the reason that it changed the color to pale yellow is because of the formation of the bromine, sorry, because of the formation of the bromine being formed there. Okay, good. And that's the reason why it changed color. So have a look at the rest and see if you can explain them. Okay, here are some displacement reactions that you can try. All right, so would a displacement reaction be able to happen with this? Of course, fluorine can displace bromine. Okay, so you would end up with sodium fluoride, plus chlorine. Okay, so just remember fluorine, chlorine, bromine, and iodine. All right, so would bromine displace chlorine? Can that happen? Let's check. No, it cannot happen because chlorine is more reactive than bromine, so for that one would be no reaction. Okay, and that's why some of the ones in the practical did not happen. Okay, and then let's look at chlorine and iodine. Of course, chlorine can displace iodine, definitely. So you would end up with sodium chloride, and you would also end up with iodine. Okay, too easy. All right, so you also need to be explaining why is it that fluorine is more reactive than chlorine and bromine. So why is it? So these are the questions that you need to be thinking about. So as you go down the group, what's happening to the size? The atom is getting bigger, and each atom needs to gain an electron in order to be reactive. So here are the electrons at equal distance need to be pulled in. Now what's pulling that in? The protons are pulling these electrons in, but look at what the protons have to be pulling through. They have to be pulling through the shells, the shields. Okay? The one that will pull the electron in the easiest is going to be fluorine because it has less shields. Okay? Good. So to summarize, as you go down group 7, the atom gets bigger. To react, each atom needs to gain an electron. The nucleus is positive and the electron is negative, so the electrons are being pulled in by the nucleus. All right. The more shells as you go down the group, so the electrons become harder to pull in because of the increased amount of shells. All right. Good. Now, if we think back to group 1, these were some of the properties of group 1. Okay. And just to end off, just to let you know that if you're doing combined science, you don't need to watch this video any further because what I'm going to be talking about is the triple science topic only. Okay, so triple scientist, now we're going to be looking at the properties of transition metals. Now transition metals, quite easy topic, very easy. All right, you just need to know that when you compare these properties to group 1 or other metals, they tend to be higher melting points, higher densities, all right, and they seem to be quite hard and strong and good conductors of electricity. All right, also they make very good catalysts, and the reason why they're called transition metals is because they can make ions of different charges. So if you think about iron, Fe2 plus Fe3 plus, look at something like vanadium. It has 1, 2, 3, 4 different charges there, transition states, and they have different colors. Because of that, they form colored compounds. Okay, good. All right, and that summarizes what you need to know for chapter 2. Now remember to check out my other videos, share my videos, like and subscribe. I'm out.